Alright guys, for this one we're looking at events in Earth's kind of geologic scale history, where we have the age in millions of years, and what I've already done is taken the log of that age in millions of years. And the goal of that is so that we can make some kind of a timeline with scale, it's going to be millions of years ago. And what we're going to have to do is do something like, well, there's 10 to the 1, and then we're going to have, so that'd be the log of 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, and 10 to the 6, I don't know, something like that. So we're talking about exponents worth of millions of years ago. Since you've already established at this point the, and I forgot 10 to the 0 in my thing, so that's awesome. So I'm going to extend my graph a little bit so we can have a nice 10 to the 0 going on there. Okay, don't do that on yours because that's terrible. And we might have event number 1, humans emerge. And at 0.69, so this is 0 and 1, that's going to be somewhere like this. That would be ape man fossils. That's exciting. Since we're already graphing in terms of exponents, so 0, 1, 2, 3, 4, 5, we are okay with dealing with the scale kind of as is. You might do this in a more exact fashion with a ruler. Since I don't have that on here right now, I'm just going to deal with this in terms of making a roughly equivalent scale for each 10 to the power of. Okay, and then rise of cats, dogs, pigs, that's at 1.57. Cats, dogs, pigs. Well, I'm really happy that dogs and pigs emerged. I really can't stand cats, although I like lions and tigers, so maybe that's an okay thing. 1.82. And a really sad note here, the dinos kick the bucket. Moving on, we've got rise of dinosaurs going backwards. 2.39 would be the exponent there, so this is 10 to the 2.39 million years ago. And we're looking at somewhere in here, the dinos rise, roar. And then going back further, so now we're at 570 million years ago, 2.76. You switch to blue for this one. This is going to be all about the vertebrates. I can't spell. First plants at 3.39 is a log age, or 2,500 million years ago. And then going even further back, we've got the Earth forming at 4.5 billion years ago, or in other words, 10 to the 3.64. Something like this would be totally fine for what you're expected to do here. We've created a scale based on powers of 10, where each power of 10 is separated by the same amount. What happens here is this gives us a place to kind of see things. What we call this is linearization with logarithms. So we've taken something that's exponential in data size and made it a little bit more workable. Okay. Similarly, we can do the same thing with the list of deaths in 1993. I made a scale, and my points that are 10 to different powers are about the same distance apart from each other. I calculated the log of each number of deaths, and those are the points that plot on the number line. Just as a reminder that when we're doing something like this, the distance between 0 and 10 to the 0 and 10 to the 1 is 9. between 10 to the 1 and 10 to the 2 is going to be 90. 10 to the 2 and 10 to the 3 is going to be 900. This is not an even scale, so even though these things look evenly split apart, the farther that you go to the right, the farther apart those numbers actually are. Hope you had a chance to check out some of those videos. They're pretty cool. I wanted to talk very briefly about what this might look like in terms of some of these problems. So we have a formula for dealing with the difference between the actual, in other words, the absolute magnitude, and the magnitude that we see, in other words, the brightness of a star. And that's this lovely up here. I'm going to do one of these problems out, and then you're going to do some of these on your own. So we're talking about Sirius, which is 2.7 parsecs. That's going to be your D value. Has an apparent magnitude. Apparent is going to be the relative magnitude. Those two mean the same thing. That's the lowercase m. And we're trying to figure out the absolute magnitude. So that's the uppercase m. So if we've got negative 1.47 minus uppercase m is equal to negative 5 plus 5 log of 2.7. Okay, I can literally type the left or the right side on the calculator. So that's negative 5 plus 5 log 2.7. We're in log base 10 because these are all powers of 10. And I get negative 2.84, so negative 1.47 minus m is equal to negative 2.84. And when I add that to the other side, divide by negative 1, we get the absolute magnitude is equal to 1.37, which is really bright comparatively. For number 23, I ask you to solve for D here. So we've got m minus big M is equal to negative 5 plus 5 log of the distance. I want to get the log part by itself first. So I might add 5 to both sides and divide everything by 5. So we get little m minus big M plus 5, all divided by 5. And that's equal to log of the distance. We know that a log without a base, that's the common log, log base 10. I'm going to rewrite this as an exponential. So we get 10 to the power m minus m plus 5 over 5 is equal to the distance from Earth. So you could plug things in to the equation here instead of having to solve for D later on. Talking about earthquakes, this is going to be using that Richter's formula where you have the magnitude is equal to the log of a over a0, where a0 is 10 to the negative 6, and a is the seismograph amplitude, in other words, how much the seismograph is moving caused by that earthquake. And what I asked you to do is to figure out some different amplitudes based on some different earthquakes. So the 2016 Ojai Peninsula earthquake, that's a 4.1 on the Richter scale. So that would be 4.1 is equal to the log of a, that's what we don't know, and that's going to be 10 to the negative 6 on the bottom. That's always the same number on the bottom. First thing I'm going to have to do is to convert this to exponential form. That's going to be 10 to the 4.1 is equal to a over 10 to the negative 6. Again, this is log base 10 if we don't have a base there. That's my base, my answer, and my exponent. Finishing this up, I got to get a by itself. So we're going to have to multiply both sides by 10 to the negative 6. And we get 10 to the negative 6 times 10 to the 4.1 is equal to A. I'm going to add those exponents together. And that's going to be 10 to the negative 1.9 is equal to A. If you want to get a decimal for that, 10 to the negative 1.9 is going to be 0.0125, and that's your seismograph amplitude. So in terms of that, that's how much the needle on the seismograph moved. And I think this is in centimeters. I don't recall. That's interesting. You might also note that for a 4.1 earthquake, what that means is that we're felt but only causing some minor damage, and that there are 30,000 of these things every year, which is crazy. You can calculate the Gloucester earthquake that some of us felt, the Honshu earthquake, and the Cape Ann earthquake in similar fashions.